Hello, everyone. In this section, we are covering correlation. So let's go ahead and get started with a couple of basic definitions here. And we're going to be discussing some variable definitions. An explanatory variable, also known as the predictor variable or independent variable, is the variable whose fluctuation in value influences a change in the value of another variable. A response variable, or the dependent variable, is the variable that has its value change as a result of the change in the explanatory value. So basically, we have some x value which changes, and we measure the response in that. That's going to be our change in y. Okay. Let's take a look at an example here, see what we mean. Consider the following data collected from a sample of NFL quarterbacks during the 2018 season regarding the number of interceptions thrown and the number of times a quarterback was tackled before releasing the ball, aka sacked. Use the data in the table to create a scatter plot that shows the relationship between the number of interceptions thrown and the sacks for that quarterback. Okay. So we have these quarterbacks and their interceptions compared with their sacks. Okay. So we see 16, 24, 12, 26, 7, 42, and so on. Incidentally, gross, 2 interceptions with 49 sacks. What a crazy person. Anyway, so let's see if there is a relationship by looking at the scatter plot. Now, a scatter plot is just where we are plotting them. Now, our first question is, which should be our dependent variable and which should be our independent variable? So here, we'll note we're attempting to use the sacks to explain the interceptions instead of the other way around. We wouldn't say that a person throwing more interceptions causes them to get sacked more. We would potentially say that somebody getting sacked more is more likely to throw interceptions. So that means our x-axis will be our sacks and our y-axis will be our interceptions. When we do so, we end up getting what's called a scatter plot. That looks like this. I simply have taken these values here and then plotted them along this axis here. Okay. And there we go. Okay. So let's see, does this seemingly indicate a relationship? Now here it kind of looks like a downward slope here, like this. Okay. So it seems to have a slightly negative slope, which is somewhat surprising. You would potentially expect it to be the reverse. Anyway. Now let's take a look at this one here. We are going to attempt to explain whether or not the points are likely to have a positive slope, negative slope, or not follow a straight line. Okay. Determine whether the points in a scatter plot for the two variables are likely to have positive, negative, or not follow a straight line pattern. Okay. The number of hours you study for an exam and the score on that exam. So let's think. As you study more, is your score likely to go up or down? It's likely to go up. So this one is likely to have a positive slope. The number of miles on the odometer of a used car and its price. Well, the more miles there are on a car, the less valuable the car is going to be. So that's going to be a negative slope. Pressure on a gas pedal and the speed of the car. So as you push down more with your foot, the speed goes up. This is a positive slope. And then D, shoe size and IQ for adults. Well, as shoe size goes up, it doesn't seem like it matters to IQ at all. So this one would indicate this is not linear or not a straight line pattern. Okay. So there we go. Now, is there a way that we can mathematically determine correlation, or a metric that we can use to determine whether or not two different variables are correlated with one another? Well, by virtue of the question, I'm sure you could probably guess the answer. Answer is yes. We're going to be taking a look at this one here, which is called the Pearson correlation coefficient. This is known as rho. So this is the Greek letter rho. Is the parameter that measures the strength of a linear relationship between two quantitative variables in the population. The correlation coefficient for the sample is R. Now we're going to be working with R almost exclusively here. So when we're attempting to say that something is highly correlated, then we would say that it has a high R. Now, R is between -1 and 1, where if it has a value of 1, it is a strong correlation, or in fact, a direct correlation. This one here is -1. This would be a strong inverse relation or an inverse correlation. And our formula here, well, using this by hand kind of requires you to take a nap halfway through. So the Pearson correlation coefficient for paired data from sample is given by, so R equals N, your sample size, times the sum of the product of your explanatory times your response, minus the product of the sum of your X sub i's times your Y sub i's. So you add up your dependent variables, add up your independent variables, multiply those, divided by the square root of the sample size times the sum of the squares of the explanatory variable minus the square of the sum of the dependent variable, or of the independent variable rather, times the square root of N times the sum of our dependent variable squared minus the square of the sum of our dependent variable. Yuck. So if you were to look at this, you multiply your X and your Y for all of them, add them up, multiply by N minus, well, it's a lot. So instead of calculating this by hand, we are simply going to be making use of our calculators or Excel. Okay. So let's take a look at an example here. Let's suppose that we are asked with finding our correlation coefficient for the following data. Where we have our age in years of children and their height. Okay. And we are tasked with finding whether or not there is a correlation here. Okay. So what I'm going to do is I'm going to go ahead and create these lists. So I'm actually going to go to math, or rather to stat edit. And I'm just going to go ahead and clear out all my lists. And start with L1. 1.0, 3.3, 1.5, 3.5, 1.8, 3.9, 2.0, 4.2, 2.2, 4.5, 2.5, 4.8, 3.2, and 5.1. Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, good. And then here, those corresponding values for each of those given inputs there. Like good old data entry to drive everyone's interest in doing these calculations, am I right? All right. So now we have those in. So all I've done is I've just filled these out. So now I'm going to go to, here we go. So you need to go ahead and press second catalog, And we're going to go all the way down to diagnostic on. Okay, so just as a little lesson for everybody here, you go to second, catalog, diagnostic on. Okay, if you don't do that, then it will not provide all the information we want. All right, let's give this a try. Calc linear regression. And there we go. So taking a look here, it shows me my R value. R equals 0.9799. Okay. So what do we see? This seems to indicate that there is a strong linear correlation. That is to say, as the age increases, the height increases. Pretty riveting stuff, right? As you get older, you get taller, at least from 1 to 5. Okay. Now, if you wanted to make use of Excel, all you do is you would use your first column and your second column. And then the function you're going to use is equals correlation here. And you're just going to go index it through. So it's A1 colon A however many data entries. Well, it went all the way to A14 in this case. And then it goes from that, and then what your other variable is. And there you go. Okay, so use the correlation feature, your first variable with your where it's starting, colon, where it ends. That'll just highlight that column there. And then you do the same thing for B. Highlight it, and everything's good to go. Okay. Let's do another one. The table below provides the number of touchdown passes and the salary in millions of dollars for some of the highest paid quarterbacks in the NFL in 2018. Calculate the correlation coefficient, remove the values for Patrick Mahomes, and recalculate the correlation coefficient. How does removing the pair of values affect the correlation coefficient, and why? All right, so let's take a look here. We are taking a look at this data. We have the quarterback of the team, the TD passes, and their salary. Okay. Oh, Mitch Trubisky. Great throwback. Anyway, so what I'm going to do here is I'm going to go to stat edit. And I'm going to be plugging these values in. So the question is, do I believe that the TD passes is likely to affect the salary or vice versa? I believe that somebody that throws more touchdown passes would get paid more. So that means that this is going to be my X. This is going to be the first one I enter. So 50, 32, 24, 34, 39, 29, 32, 19, 35, 32. And I'm just going to enter these in here. All right, there we go. And stat, calc, linear regression, calculate. Let me just make sure that I've got these lists in properly. 50, 4.1064, 3, 25, 24, 7.2181, 34, 21.85, 39, 24.594, 29, 15, 32, 20.8125, 19, 6.3378, 35, 30, and then 6.9844. Okay. Just like to double check. All right, so I find my R value here. So now let's take a look. How does this change if I remove Patrick Mahomes? So here it seems like there's actually a slightly negative correlation here. Looks like the more touchdown passes you throw, the less your salary is ever so slightly here. But we were told to go ahead and remove Patrick Mahomes and see what happens. So I'm going to go to stat edit, and I'm just going to go ahead and delete this entry, delete this entry. Now let's see how this affects it. Linear regression again. And now I find that R is 0.1463. So when I take a look here, I'll note, hey, it was 0.13 negative. So here it seems like it went from a negative correlation to a positive correlation, removing that. So the question is, why did that end up adjusting the result? Well, I can see that when I take a look here, it no longer has this skew from that individual data entry, okay? And that found that now we've got a positive correlation here because this was affecting it. So again, let me just go ahead, just make sure that all my value, this actually should be 32. I thought something was wrong because I got something a little differently than last time. All right, so let's go ahead and recalculate it now. There we go. So now we get R equals 0.7713. And this is why I include this stuff in my videos, just to show you that anybody can make mistakes on these. You just need to double check and make sure that you're going through these, okay? Small little errors like this do pop up. So we see that we went from a not very high correlation to a very, very solid and robust correlation of 0.77. So it seems to indicate that Patrick Mahomes is something of an outlier influencing the results, okay? So it goes from a pretty weak correlation to a very strong positive one. It's a very, very low salary, very, very high touchdown. So he's going to be affecting that ratio quite a bit, okay? Now, when can we determine whether or not a correlation coefficient is statistically significant? And we determine it if the absolute value of R is greater than or equal to R sub alpha. Okay, so for that, what we need to do is we need to go ahead and compare this with our R sub alpha, which we can find in our coefficient table, which is going to be defined by our N and our alpha. So let's take a look at an example here. Use the critical values in the Pearson correlation coefficient table to determine if the correlation between the number of passing touchdowns and base salary from the previous example is statistically significant using a 0.05 level of significance. Okay. And for this, I take a look in my table and I find for N equals 10 and alpha equals 0.05. My R sub 0.05 is going to be 0.632. Comparing that with my previous result, I would find that my first one is not statistically significant. Now, after I remove Patrick Mahomes, I now have N equals 9, and my alpha is still 0.05. my R sub 0.05 in this case is 0.666. Spooky. And my previous one was 0.7713. I'll note 0.7713 is greater than 0.666. So this one here is statistically significant. Okay. And there we go. So this relationship was not a statistically significant correlation. This one was a statistically significant correlation. Okay. Now, if we want to test linear relationship for significance using our hypothesis testing, we will have our things here. And now these are going to be with respect to rho, our population correlation. And our alternate hypothesis for this is that there is no linear relationship. Okay, so rho equals 0 will always be your null hypothesis for these. Your alternate hypothesis is going to depend on your test. So you have rho does not equal 0. This is for your two-tailed. And if rho does not equal 0, what that means is just there is a significant linear relationship. It doesn't tell us which direction it is, though. Our other one might be that rho is less than 0. This is our left-tailed. This tells us that there is a significant negative linear relationship, which is to say that as one value increases, my other value decreases. And then rho is greater than 0. This is my right-tailed. And this, of course, is telling me that there is a statistically significant positive relationship. That is to say, as it increases, the other one will increase as well. Okay. Now, our test statistic formula is going to be given to us here, noting that we are going to be making use of a t-test. And t equals r over root 1 minus r squared over n minus 2, where r is our sample correlation coefficient, n is the number of data pairs we're looking at, and the number of degrees of freedom is n minus 2, noting because we have two variables here. Okay. So for these, we are just going to be comparing our t value here. One thing that I should note is that, let me actually just go ahead and copy this directly here to make this explanation a little easier. So if we're looking at a two-tailed test, we're going to compare the absolute value of our test statistic t with t sub alpha over 2. And for our others, we're just going to look if t is less than or equal to negative t sub alpha and t is greater than t sub alpha. So note t sub alpha over 2 for our two-tailed test, and we're testing for the absolute value of that. Okay. All right. So let's go ahead and take a look at some examples here. At least one. Use a hypothesis test to determine if the linear relationship between the number of parking tickets a student receives during a semester and the student's GPA during the same semester is statistically significant at the 0.05 level of significance. Refer to the data presented in the following table. All right. So we want to determine, is this a statistically significant relationship? So if we're just testing if it's significant or not, that's just going to be my two-tailed test. So I'm going to test, is it different than 0? Okay. So again, because we're just determining if the relationship is statistically significant, I just want to know if my alternate hypothesis, rho is not equal to 0, is true. Okay. Again, note my alpha here is 0.05. Okie dokie. So I'm going to go ahead and start by turning it back on, stat, edit. clearing these out, and just plugging in my values. 0, 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 5, 7, 8. Now, if you're using Excel, usually your homework will allow you just to be able to export it directly. So whether or not you want to do that is up to you. 3.6, 3.9, 2.4, 3.1, 3.5, 4.0, 3.6, 2.8, 3.0, 2.2, 3.9, 3.1, 2.1, 2.8, 1.7. And let's just make sure we've entered all these correct. All right, everything looks good here. So now I'm going to go to Stat Calc, linear regression. Taking a look here, I find that my R equals negative 0.586619. And here, I'm just going to round to 6 places, just because it's an intermediate calculation. This is not what I'm looking for here. I'm looking to find my test statistic. So now I'm going to use my formula here for my test statistic. So it's R negative 0.586619 divided by square root of, and it's 1 minus R squared okay, that's my numerator, so I'm going to close that with a parentheses here, divided by my sample size 15 minus 2. And I get that T is approximately negative 2.612. Okay. So now what I'm going to go ahead and do is I am going to find in my table T sub alpha over 2, which is T sub 0.05 over 2, which is 0.025. And if I look at my T distribution table for degrees of freedom equal to 13 here, note that your degrees of freedom is not just n minus 1 here. Degrees of freedom is n minus 2 for these. So my degrees of freedom here is 13. So taking a look here in my T distribution table, I get 2.160. Okay. So I'm going to take a look. Is the absolute value of negative 2.612, is this greater than or equal to 2.16? The answer is yes. So here we reject our null hypothesis. Okay. So just to follow up what we did here, we calculated our T, and I calculated my T by making use of my formula here, which is R over root 1 minus R squared over n minus 2, where this, of course, is my degrees of freedom. This gave me what my T was equal to. I'm looking at a two-tailed test, so I compare this to T sub alpha over 2. In this case, our alpha is 0.05, so our alpha over 2 is 0.025. And I look in my T distribution table for my degrees of freedom 13 and 0.025. I find that this corresponds with 2.160 for T. That tells me that then I compare the absolute value of my T with this T sub alpha over 2. Since it is greater than or equal to it, per this, I reject my null hypothesis. So that tells me that I accept my alternate hypothesis, then that there is a statistically significant relationship. Note, I am not saying whether or not it is positive or negative. I am simply saying that a relationship exists. Okay. So then our final concept here is that of the coefficient of determination, otherwise known as R squared. The coefficient of determination, R squared, is a measure of the proportion of the variation in the response variable that can be associated with the variation in the explanatory variable. Okay, so it's the proportion of the variation in my dependent variable that I can associate with my explanatory variable here. Okay, so for example, if the correlation coefficient for the relationship between the number of cups of hot chocolate sold at an outdoor skating rink and the average temperature outside is R equals negative 0.65, how much of the variation in the number of cups of hot chocolate sold can be associated with the variation in temperature? So what that means is I can go ahead and take my negative 0.65 and square it. And this tells me that R squared is 0.4225 or 42.25%. So that means approximately 42.25% of the variation in the number of cups sold can be associated with our variation in the temperature. Okay. But these are all the types of examples I wanted to show you in this section. Be sure to let me know if you have any questions as you're working through these at all, be it just actually substantively or getting your calculator to work. Otherwise, I will see you in the next video.